You want to share any screen from your point?
Yeah, I can share and we can test it out.
Quickly check, yeah.
Test.
I see few student leaders present here. Kindly I request you to, ask your other students, participants from your college to join in fast. The speaker is here and we'll be starting on time. Nida Basu, I see Kamuru Nisa.
Can you see my screen?
Said started sharing, not yet. You go to the next slide. Sometimes it takes, just go to the next slide. Suddenly it will start appearing.
Nobody can see, is it?
No,
I can't.
It just says it has started sharing screen, but it is not.
Okay, that's weird.
It's not visible.
1 second.
எனக்கு கிடைக்க மாட்டேங்குது.
Yep.
Now we are able to see.
Are you seeing the slideshow mode or are you seeing the PowerPoint?
The slideshow mode.
Slideshow.
Mode.
Go to
Can
the
you
You're
go
seeing
down?
it in full
Go to
screen,
the next
right?
slide.
Okay.
Go to the next slide.
Just go to the next slide so that we can see the flow.
Only the first one.
First slide. Yeah. Yeah, got it.
Yeah.
Super.
Yeah.
Only seeing one slide at a time, right?
Yeah.
Yes, we are not seeing the sorter and all that.
Yes.
Got it.
Okay, great. So then we'll leave it like this, I think.
But for me, the transition is very slow. I don't know about others.
Okay.
Maybe it's we can do nothing about it. No control.
I'll talk a lot, so the transition won't matter anymore.
No, I don't know if the PowerPoint has a lot of graphics in it. So.
No, it doesn't. Not a lot. You can see the first slide with the title, right?
Yep.
Yes. Yes.
Okay. Shall I just leave it like this or should I just close? I don't know if somebody else is going to show some
Can
slides.
be there, not a problem.
No, nothing.
Okay. So I'll just leave it like this. Okay.
I'm not able to see. I'm seeing only Subbu full screen.
I'm just turning off my video. I'll join again in about 10 minutes.
Okay.
சுஜாதா நீங்க வந்து நாளை மீட்டிங்க்கு வந்து இன்வைட் அனுப்பிச்சிடுறீங்களா டீம்ல?
Sorry, I'm muted. I didn't realize that I was muted. I said I'll do that.
Yeah, நாளைக்கு அனுப்பிச்சிருங்க. இப்பயே அனுப்பிச்சிருங்க, இது முடிஞ்ச உடனே. இல்ல இப்பயே கூட அனுப்பலாம்.
I'll do that.
ஏன்னா RKR எல்லாம் ஒத்துட்டா. அனு, if time permits, she can join. Other, I have her inputs anyway on the mail. That's not a problem.
Sure. I have that same time I have another meeting.
If possible, you join. Otherwise, I will take the notes. No problem.
That is only 20 minutes actually.
Sure, I leave it to you. எப்போ முடியுமோ join பண்ணீங்க. No problem.
I will jump from there and I will join.
Sure.
Requesting the student leaders who are here with us today, please touch base with the participants who have registered from your college and ask them to join in. It's almost 4:21. We have 9 minutes. If they are joining in the YouTube also, it's fine.
இதில் 500 இல்லையா Zoomல?
Yeah. Robin and Lamna, just check if we are. I have already gone live, so just check.
It's live, ma. Already it's live.
Yeah. Right now, 13 viewers there. Okay. And Robin, just start the recording. Thank you, Manavar. Thank you, Nida, for confirming that they will join.
Shall I start the recording or?
Okay, you can start at 4:30. Professor Srinivas Rao from EC Alpha, is it? Dr. Srinivas Rao?
Yes, ma'am. He's from Alpha.
Good evening, sir. Dr. Srinivas Rao. Should be able to unmute. Robin, you have the quiz link and the feedback link with you, right?
I have.
One of you will paste it.
Yes.
Is there a wind sound coming?
wind sound வருதா? சரி, இப்போ வருதா பாருங்க. நான் மியூட்ல போறேன். இப்போ வருதா பாருங்க. இப்போ நான் மியூட்ல போறேங்க. இப்போ வருதா?
இல்ல இன்னும் மியூட்டே ஆல. அதான். இப்ப வரல. No, it's not there.
நான் மியூட்ல போயிடுறேன் அப்புறம்.
Fan. Okay. Sujata, somebody was raising their hand.
I mean, they are periodically raising and dropping. So I think they're just trying something. Abhishek, is there anything that you have to say? Abhishek?
Abhishek Dhaneshwaran.
Is there anything that you wanted to say?
Ask him to unmute and varda unte. Hello, sir. Mr. Prabhuram from Ramco has joined in. Faculty and I think IC Nanik. IC or EC?
Tata, ma'am.
Cholupa, Robert.
Last 100.
Yeah, 30. We'll have Subramanyam coming in.
Dr. Subramanyam, are you there?
Yes, I am there.
Yeah.
Okay. So,
We'll start.
do we get started?
Yes. Yes.
Yeah, we can.
Yeah.
Okay. So, good evening, one and all. It gives me an immense pleasure in welcoming all of you to the first Theory to Practice lecture series for the PALS 2020-21 edition. My name is Sujata, and I'll be your virtual host for the next 2.5 hours. As the name suggests, Theory to Practice, or T2P, as we fondly call it, has two components, the theory part and the practical part. And this makes it different from the regular Aspire or Acquire events that you may have attended, few weeks back. And I'm sure those of you who have attended this lecture earlier definitely will be having some nostalgic memories of attending this session from the IIT Madras campus. But again, this year is a very special year, and with a determination that the show must go on, here we are conducting this session in the virtual mode. On behalf of the entire PALS family, I wholeheartedly welcome Dr. K Subramanyam, Executive Director of Power Gear and the speaker for the day. And I also welcome the management, faculty representatives of PALS Partner Institute, any EC members and student leaders who are present here. Warm welcome to the PALS members. And last but not the least, welcome my dear past student participants. Before we jump to the session, a few known ground rules which you have been hearing all the time. All of you will stay muted. Kindly do not turn on your video. We have noted questions from the registration form, and during the Q&A segment, we will have it answered from the speaker. However, if there are any more questions, we will take them through the chat window. And our customary note, kindly log in your attendance in the format mentioned in the chat window. For the YouTube users, please log in there in the live session chat. And at the end of the session, we will circulate a feedback form. Kindly stay back till the end, give your feedback before you log off. I now welcome Ms. Anuradha, PALS champion, to deliver the introductory speech. Over to you, Anu.
Mute.
Anu, you're on mute.
Hello, everyone. Good evening, and welcome Dr. Subramanyam yet again to another session with the PALS students. And I was supposed to introduce Subramanyam, but I had a sneak of his slide. So I have something written here. I will add, and he will probably add on to that. He's a good friend of PALS, and he had been with us through in several occasions RSW, and he has always said he would like to do some serious stuff. And as students, we may take different routes. One is to the higher education, and the other one is research opportunities, and the third one is on your own or into some industry. But here we have a person with us who has done his, who has obtained his PhD from Cornell University in electrical engineering with specialization in MEMS, not memes like you guys, MEMS, micro electromechanical systems, or MEMS. He obtained bachelor's degree in mechanical engineering from IIT Madras, and he is currently the executive director R&D at Power Gear Limited. We had been to this place for the faculty. We'd been visiting Power Gear, I think, once in 2 years or every year. And he has been a wonderful host, talking about how contract research is done for big companies and how we have showcased our ability as Indians to other countries, rest of India. And we have and he has a wonderful background. You can go to his LinkedIn and check it out as well. He's been with GE Global Research, and as a young researcher, he had got the award, Hull Award, and Whitney Award, and he managed a large program on MEMS at GE and received 2 prestigious awards for the research. One of them, the Hull Award, is presented to early career researchers at GE Global Research. The other award is Whitney Technical Achievement Award. Please go and look it up, what it is all about. And he has over 50 plus patents to his credit, and he has naturally contributed to several publications, research publications, and he's an avid researcher. He also headed the Innovation Summit at Tamil Nadu, which was held in CTC last year, I think. So, adding on to that, and I have great pleasure in inviting Dr. K Subramanyam to address the gathering, tell them what is the route they take from research or an idea to a project or to real implementation in the real world. Dr. K Subramanyam.
Thank you, Anu, and thank you to everyone in PALS. Can you hear me clearly? Is the audio clear to everyone?
Yes, please. Yes.
Yes, Dr. Subramaniam.
Yes. Okay. Thank you. I just wanted to check that up front. So as everyone said today, and Sujata said, I think it's almost a nostalgic memory of doing these lectures in SAC and CLT at IIT campus. So it's a big change, and also want to give a disclaimer that because it's all online, we will have the usual trials of online lectures with disturbances in the internet connection, etc., etc. But please put up with all that. It cannot be as good as a live lecture. So we have to do our best given the circumstances. And I'm assuming that there are a lot of different colleges who have joined today, PALS member colleges. My goal is you have to take away something from this lecture. So it doesn't matter if the audience does not understand everything that is shown in the lecture. I have tried to keep it as lucid as possible, but also as technical as required. But if there are at least 1 or 2 takeaways, then I will be a very happy person. And as Anu said, I have been a friend of PALS, a pal of PALS in some sense for a long time. And it is my privilege to be giving this lecture on behalf of PALS. So with that, let's get started. So the topic, of course, is T2P. T2P is theory to practice. It is also technology to product. So I've taken the liberty of using the pun, I think, as intended. So it is, so whenever theory goes to practice, technology goes to product. So I believe it's the same thing. So with that in mind, we are going to talk about taking R&D to product in the real world. And this is something that sounds extremely simple when you first read that line, but it is anything but simple. In fact, the reality in industry is that the latter phase of R&D, where it goes to product from the idea or from the prototype, is usually the more difficult phase. So in other words, we are actually saying that the innovation part, inventing a new idea, proving that it works, while it is challenging, is actually easier than the latter phase where you have to take this idea to a product in the real world. So we will talk about a few simple mantras, if you will. And I've kind of listed it in the form of mantras because it is easier to remember that way and easier to relate to for that. So just before that, I have one slide, which is,
Is the
and I
screen
hope
shared?
everybody is seeing the
Yeah.
slide. Can you see the slide changing? No.
Yep.
Yes,
Yes.
Dr. Subramanyam.
Okay, thank you. So this slide is, of course, there's already been an introduction. So the point of this slide is not to introduce myself again, but purely to show you the diverse breadth of experience which has led me to where I am today, right? So that is just the intent. So I started with IIT Madras as a mechanical engineer. I moved to Cornell University in the US for my master's and PhD as an electrical and computer engineer. The reason I switched fields was, as Anu talked about just now, I was working in the field of micro electromechanical systems, which was a very multidisciplinary field, and it cut across electrical and mechanical engineering. And I had to change fields, which in hindsight was a great thing to do. Then I actually worked for McKinsey in the US, which is in the management consulting side of things. I worked there for a short time. Then I came back to research. I worked for General Electric, GE's Global Research Center. There I worked on so many different technologies. I worked on sensors, I worked on power systems, I worked on appliances, I worked on lighting, so many different areas. So many successful R&D projects taken to product, because being an industrial research lab, the whole idea was to do research which can make money for the company, to be brutally frank, right? So that's the main mantra of any kind of industrial research lab. You can do a lot of fundamental science, fundamental ideas, innovation, and all that. Finally, it has to make money. So it is not about just the pure joy of pure research, right? So as part of this, there are many patents that came out of this. Most of these are international patents, right? So all of that was an outcome of this. And then after that, I returned to India about 10 years ago. So it's been a little more than 10 years since I came back to India and started working for Power Gear, where intentionally I branched off into production and supply chain. So I managed a factory for about 3 years before I came back into R&D. This was to get my feet wet into real world environments, because there is a common complaint among production people that research people live in a world of their own. So we need to understand the other side also, in terms of how production works, what the pressures are, what customers ask for. All of that was a great experience. And then I started within Power Gear what I believe is India's first contract R&D organization, or rather industrial contract R&D organization, because academic institutions like IIT also do a lot of contract research. So we through this, we worked with many companies. We became the extended research lab of companies such as Boeing and Bosch and Tata and Schindler and many companies like that. We have a team of scientists who supplement research efforts at all of these companies. And of course, many awards for research as part of this, and some of those awards explicitly for taking research to the market, right? So which is a very important part. So as I said, just showing all this, not to talk about myself, but just to show that everybody needs this combination of experience, where academia is important, industry is important. Industry is important on the R&D side of things and on the real world manufacturing side of things. So all of this gives you a different flavor of experience, which adds up. So with that, let me get into the mantras, which I was just mentioning, for how theory goes to practice, how technology goes to product. So yes, I hope the slide changed.
Yep.
Okay. So this is a very simple example that I often use. I've used this in previous lectures also. The first mantra is what we call think in reverse. Okay. So where it is a common trap for a lot of scientists, a lot of even students or faculty or whoever it is, to work on our pet idea for innovation. So when we feel strongly about a certain technology, when we feel strongly that something needs to be done about a certain need, right? Then we go and work on that idea. So this mantra is the exact opposite. So what we are trying to say is we should not give in to that temptation. We should work in reverse. In other words, rather than working on our pet idea and then potentially later on complaining that nobody from the industry is picking up that idea and making a product out of it, we need to work in reverse, which means we need to go to the final customer, whether it's an industrial customer, whether it's an end customer who is an actual consumer, who is a normal person on the street. We need to start there and ask that customer as to what are the pain points, what is the need, what do they want, right? So let's say you're doing a project for an energy company. What is really hurting you, right? What innovation do you need? If you're doing a project for an electric vehicle company, right? What is the biggest issue in electric vehicles today? Why are you not able to sell electric vehicles? What issues are vehicles coming back with from the field, right? So that is the first question that you ask. And then from there, you work in reverse, right? So let us say somebody, let's take the electric vehicle example. Let us say somebody says, my biggest issue is with the mileage I'm getting from the electric vehicle. I need a better battery on this vehicle. So that creates a problem definition for you. And then you kind of sit and brainstorm. If you have a team, you brainstorm as a team. If you're an individual, you brainstorm as an individual. You figure out what you can innovate to solve that problem, right? And if somebody wants a better battery, it could be a chemistry problem. It could be a vehicle problem where you do weight reduction on the vehicle. There are so many ways to solve that one problem, right? So here, it's very, very important. And throughout my industrial career in research, we were asked to sit silently when the customer talks. And we were asked not to influence the customer explicitly, right? So we could only ask some questions in order to clarify what the customer is saying. So the customer has to come and describe to the scientists as to what their need is. As to what their pain point is, what will sell in the market, because the customer knows the market best. The innovators, the scientists are not necessarily the people who know the market best, right? So for example, we were working with a company that makes these lifts, elevators. And then we were thinking that, okay, elevators are fairly mature technologies. And what kind of innovation could they want? And if you think about it, we were thinking, okay, maybe they want faster elevators, maybe they want cheaper, more efficient ones, things like that. But when we actually asked them, they said, all of that is easy for us. But what we want is, given the COVID situation, people are afraid to touch the buttons on the elevator. So we want a sanitization solution that every time somebody gets in and out of the elevator, we want to sanitize the button automatically. They said that is the biggest problem for us. So that defines the research problem. Then you start thinking of technologies that can serve that need, right? So always think in reverse. First find the application, first find the market, then innovate to meet that need. So what happens automatically if you do this is, once you finish innovating, once you have a prototype, once you have a demonstration, then somebody will pick it up because it was a relevant need in the first place. Somebody will pick it up, somebody will sell it, somebody will make money out of it, right? So here I have given a simple example. There is a problem in the electrical industry, and Power Gear itself is in the electrical industry, in the energy power industry, where we use a lot of copper. And copper costs money for power distribution because copper is an expensive metal. And a lot of copper is used in electrical distribution because copper is the core material from which a conductor is made. Right? It is one of the best conductors. Of course, silver is better, but silver is extremely expensive, so nobody uses silver really. Copper is the most commonly used. It's a good balance of cost and conductivity. So copper costs a lot of money. So any electrical application that you make, you will need to move current from point A to point B, and that needs copper, right? So an electrical industry had come to us with a very simple question, saying that copper costs a lot of money. Please reduce the amount of copper in the equipment that we are making, right? And even if you take a simple apartment, a flat, right, you will be astounded if you actually look at how much copper they use in the wiring. Every plug point, every light fitting, every fan fitting, every other appliance needs a copper wire that goes, not just one copper wire, but two copper wires, plus and a minus, which goes to that point, right? And if you have to wire a simple light that is hanging from a bulb that is hanging from the ceiling, you need to wire not only that bulb, but also a wiring all the way to the wall where the switch that controls the bulb is situated. So there is a lot of copper that goes into this. So the way we had solved this is, of course, once we had listened to the application and we have been given this problem. It sounds crazy at first because how can you reduce the copper? You need a certain amount of copper to carry a certain amount of current, right? So we tackled the fundamental science. We asked ourselves the question, how much current can you send through a piece of copper wire, right? And intuitively, people would think that the bigger, fatter the wire, the more current you can send through it, right? And I'm not going to dwell too much on the science, but if you literally think through the fundamentals, you will realize that that assumption, even though it sounds intuitive, is actually wrong. And there is no direct correlation between the size of the wire and how much current you can send through it. And we had realized that this is actually very much a thermal problem, where if you can maintain the temperature of a wire, you can actually send a lot of current through the same wire. So it's all about how a current carrying conductor is cooled. So if you can do a very good thermal management system, if you can have the right heat sink, if you can have the right heat dissipation mechanism, right? That alone will actually help you send a lot of current through a much smaller quantity of copper. Because the limiting factor for how much current you can send through metal is not the number of electrons, it is how well you can dissipate the heat that is generating out of it. So this gives you a very interesting research problem, right? How do I design normal current carrying systems with very good thermal management, right? And the result of that is some application pain point that somebody had, where they just thought that they wanted to reduce the amount of copper that is used in the industry. And this is something that we could deploy into the field, and this is something that really works. Simple things, and I'm not talking about cooling with an air conditioner or liquid cooling or something. Simple things like changing the shape of the conductor to make it have fins, for instance, right? Will enhance the heat dissipation to a point where you can actually start with a lot less metal in the first place, right? So I hope this mantra is clear. So just to summarize this, we always think in reverse. We ask the customer what the application is, what they want, right? And then we work backwards from that and we ask ourselves as to how we can innovate to solve that specific problem. So automatically, once the project is done, once the innovation is done, the application is already waiting, the market is already waiting. Okay. So I'm just going to the next one. The next mantra is multidisciplinary. Okay. Multidisciplinary simply means that today, individual disciplines are saturating in innovation. So if you're just a mechanical engineer, if you're just an electrical engineer, I'm intentionally using the word just, it's not in a derogatory way, but if you're a pure mechanical engineer, pure electrical engineer, there is a lot of innovation that has already happened. And to do more is a little more difficult today. So when there is a team that is formed out of people, scientists, whatever, of different disciplines, right? It could be, for example, I'm currently working with a team which is a combination of mechanical engineers, people in the pharmaceutical industry, and third, people in the materials domain, right? So the combination of all this sounds crazy. I mean, how will they come up with a project, right? But there are real world applications that require a combination of these kinds of skills to come together. Okay, and this application I'm showing here is an international problem. There are thousands and thousands of kilometers of pipelines around the world. Pipelines carry so many things. They carry oil, they carry water, they carry gases, they carry all kinds of things. And corrosion in these pipelines is a major issue. And there are things called PIGs, PIG, pipeline inspection gadgets, which are robots which travel through thousands of kilometers of this pipeline, and they inspect these pipelines in the process. The whole thing takes months or years to even finish one pipeline, right? So it's not at all an easy process. It's a major problem. Corrosion costs the world several $billion a year, and it's really a major problem, right? So how do you build systems, these pipeline inspection gadgets, which detect corrosion in these pipes, right? And if you look at the skills of this slide is specifically about how to be multidisciplinary, you will need, for example, electromagnetics, which is the way you sense these defects. It could be electromagnetics like infrared radiation or some other frequency, or it could be ultrasound, right? Which is more of an acoustic wave. It could, you will need optics because you will need cameras. You will need to image these places. You will need to do image recognition, automate, because no human being can manually scan so many images. You will need robotics because you will need these gadgets to travel, to essentially swim through the oil or the water through so many kilometers of pipeline, right? And you will need electronics, of course, because all of this has to come together and it has to transmit the data. You will need controls because this thing you will send it into the pipeline, but how will it come out, right? The worst case is if it gets stuck, then you're in deep trouble. So controls are very important. The feedback that this is getting, it should not get stuck. And if it does get stuck, it should be able to communicate where it is and somebody should be able to bring it out. And then last but not the least, something that is hugely underestimated is a system integration skill, where somebody who knows all of this is part of the team and is able to put all these skills together and make a product, right? Make a product where the electromagnetics, the optics, robotics, mechanics, everything works in one piece. So that's the system integration part. So just to show you, just a simple application, sounds simple at first, just how do I detect corrosion in a pipe, right? The whole problem definition sounds very simple. But if you look at this kind of skills that have to come together, it is impossible today for a person with a single one of these skills to do this project. You need literally a team of half a dozen skills at least to make something like this happen. And it's something that even sounded simple, something that sounds complicated, forget it, right? It needs a huge number of skills. So one of the teams I was running at GE in the US had about 35 people in it. Each person had a different skill. Each person had a different skill. And you would think, are there so many skills in engineering, right? There are. So there are so many skills, subspecializations, all of that are there. So I hope this point is clear, and let me move on to the next one. Okay. Next one, the next mantra is how to be product oriented in research. Okay, because a lot of students, faculty, scientists have the tendency that the research problem has to be a cool sounding problem. It has to be a very interesting problem. But we have to be very grounded to the product. And what I mean by this is there are criteria in the research problem that are beyond technical criteria. These are criteria such as cost, such as reliability, right? What is the supply chain? So if you look at the last two lines, it is talking about those kinds of criteria. So in most projects, you will have to worry about these things, right? Unless you think about cost, early on when you're inventing itself, unless you think about supply chain. Supply chain means who's going to provide some of the components, right? Is the supply chain, does it exist? Do I have to create a new supply chain? Thirdly is the manufacturability, right? You may invent a very nice exotic material or a process, but is it manufacturable? Is it cost effective? All those questions are important. Packaging. And when I say packaging, it means so many things in so many different applications. But an example I like to use is if you take the example of a sensor. Let us say you make, let us say a pressure sensor, which is a very common type of sensor, right? A pressure sensor is designed to measure pressure, of course, right? And a very classic example is pressure sensors in marine applications, okay? So if you put a pressure sensor straight away into seawater, it will corrode in no time because it is salt water, and salt water corrodes almost everything. So what people do is people encapsulate that pressure sensor in a stainless steel package. Stainless steel does not corrode. If you choose the right grade of stainless steel, it does not corrode in salt water. So when you package it in stainless steel and then you immerse it in the seawater to measure the pressure of the water, how does the pressure get transmitted to the sensor? The sensor is inside the package. The sensor has to be able to feel the pressure in order to measure the pressure, right? So it's a very tricky problem because you have just isolated the sensor from the environment to protect it, but you need to expose the sensor to the environment because it needs to measure something in the environment, namely in this case pressure, right? So how this works is they now have to modify the package, right? So the package has to have some kind of a diaphragm or a membrane which deflects in response to the pressure of the seawater. Then they fill the package with oil because that deflection of the stainless steel membrane will be transmitted as pressure in the oil. And the sensor that you originally made in the first place will be sitting immersed in that oil so that it will feel the oil pressure. So rather than feeling the seawater pressure directly, it will feel the oil pressure. Okay, so oil is, and fluids are normally used because fluids are incompressible. Fluids are used to transmit pressure in many applications. So what happens is, let us say now there is an extraneous factor like temperature. Okay, temperature is a very common environmental factor, and temperature, let's say, is changing. Today it is 20 degrees, tomorrow it is 35 degrees. And temperature is changing. So when temperature changes, you have different materials now in this package. You have stainless steel, you have oil, and you have whatever material you have made the sensor out of. And when you have multiple materials, there is a differential thermal expansion due to the temperature change. And this thermal expansion will appear as stress. And that stress will be measured as pressure. So a change in temperature will now look like a change in pressure. Now, how do you tackle this? Right, which is why I'm not going to answer this for you right away because it's a big answer. But what I'm trying to say is packaging is actually means a lot in many applications. When I say packaging, it is not just wrapping it in gift wrap paper, right? So packaging is how do you encapsulate what you're making, and how does that talk to the environment through the package? And sensor is the most classic application for this because, as I said in this pressure sensor example, the minute you put a package around that sensor, then the performance of the sensor itself changes because of the package. It is influenced by the materials in the package. So it is not enough to just design a sensor. It is important to involve the package right in the concept phase and include the errors that the package is going to include in the is going to create in the measurement, and design the sensor to include all of those errors. Otherwise, we will realize that in the final stage of the project that when you try and package and actually make a real measurement, it's not going to work. Right? So all of this, cost is important, supply chain manufacturability, right? Where, unless we think about all of these in the early stages, then the project is doomed. It will fail in the later stages. Another important thing is reliability. Reliability talks about how something fails. And this is, again, something that is done upfront in research projects, where there is something called an FMEA, failure mode effects analysis. So we brainstorm, we list out as a team how all our project can fail, right? It could be technical, it could be cost, it could be whatever, right? And then we put in the impact of that failure. How important is this failure for the product? Will it make or break, or is it something that we can tackle? And at least at the back of our mind, we know how this is going to fail, and we will design around it, right? An application which I'm showing on the top of this page here is, you may have heard a few years ago that one of the ISRO failures, ISRO, where the rocket was launched perfectly fine. There was a very nice satellite which was tethered to the rocket. The satellite had to release from the rocket at a certain appropriate time. And that particular incident was, everything was fine, except the satellite failed to detach from the rocket. And you can look this up in the news, you will get some detail about it. But this was a very simple mechanism that the satellite was tethered to the spacecraft through a rope. It was just a rope. And there was a small micro heater, a small heater basically, which was supposed to burn off that rope at the right time. So it was as simple as that, nothing fancy, right? But it didn't happen. And that is reliability. So such a simple mechanism, or something is supposed to heat up and burn off the rope and the satellite detaches. If that didn't happen, then there is an issue with reliability. And this is a very specialized example of reliability where this whole mechanism has to only work once in its entire lifetime, but that once it really has to work. It cannot fail, right? So reliability, the science of reliability as to how you predict the failure modes, how you simulate the failures, actually subject your prototype to those failures. Custom ALT is what is written in the slide. ALT means accelerated life test. So you accelerate that failure. So there are certain failures that may take 5 years, 10 years, 20 years to happen. You can't wait for 20 years to test it. So you have to find the physics that accelerates it. Sometimes if you run the product at a higher temperature, certain failures will accelerate. Sometimes higher humidity will accelerate. Sometimes higher current will accelerate. There's so many factors depending on the nature of that product. Okay, so I'm just moving on to the next mantra. Before I get into case studies, I will show you some interesting case studies after this. So the next mantra is the business case. Okay, so this sounds, again, something that sounds simple. And if we did the first mantra, which is think in reverse, you would have addressed some of this at least. Okay, but it is also an independent factor that is very important in taking a theory to practice or technology to product. And I've just broken this down into 4 simple things. The first one is the patent landscape. Okay, and this is not to be underestimated. A lot of people think this is trivial. Always, when we start a research project, we look at what is out there in terms of patents in that technology space first. It is done for 2 separate reasons. One reason, of course, is that who has already patented some technologies in this space, because you cannot copy, which means you will be infringing on those patents. So that is one reason why you do this. Second, which is the second bullet, which is clubbed along with the first one, is called white space analysis, which means once you do this patent analysis, you find out where all people have patented. Okay, so as let's say you're making a bigger, better battery for electric vehicles, you survey the patents. Who is working on what technology, right? And then sometimes you will come up with a gap. You will realize that in some spaces, in some technologies, nobody has done anything, or people have done very little work. And that is what we call white space, which is guiding you to innovate now. So you find that a lot of people have worked on lithium ion, a lot of people have worked on other lithium chemistries, but you may find that in some other chemistry, there has been very little work done, but it may still hold some potential as a competing technology. So that becomes a white space, and that in turn guides you on which area you can concentrate in terms of innovating a new technology. Okay, so third one is voice of customer. Voice of customer simply says that you have to listen to the customer. So, but this is a formal process that most industries do. So whether it's an end customer who's a typical consumer, or if it's a business to business, B2B kind of thing, where it's a business customer, you have to sit and listen to them, try and figure out what are all their issues, and that becomes the voice of customer, and that again defines the specifications for what you're going to innovate. Fourth one is timelines and deliverables, and this is something again that people are totally relaxed on in terms of innovation. People think that innovation cannot be time bound, but that is just not true, because what happens when you think in reverse is that there is already a date fixed for launching a new technology. So let's say 3 years from now you're launching a new technology, and industry will fix that date, and then everything else happens backwards from that date. So it's very important to plan a research timeline. So let's say you're launching in three years. In 2 years, you'll have to finish your research, which means that in year one, you'll have to finish certain tasks. In 6 months, you'll have to finish certain tasks. In 3 months, you'll have to finish something, right? So, and all of this, even with, so let's say you define a 2-year research program to hit a 3-year product timeline. Even within that 2-year program, believe it or not, the way industrial R&D works, even within that, it happens in reverse. So how we do it is we show a demonstration in the very first 6 months, and then we work on the technology. And that sounds crazy, I know that. But what we do is, because what we do is in the first 6 months, nobody is patient. They need to see a touch and feel demonstration. They need to see something working. So we just pull in whatever is available off the shelf. It may not meet the exact requirements of the products, that new technology, but we pull in whatever we can find off the shelf. We put together a prototype. It may be large, it may be bulky, it may be ugly looking, nobody cares. But it will be a touch and feel demonstration pretty close to what the customer wanted, right? And then once people see that, then they will have the appetite to continue the funding for the research programs. And then in future months is when we go into the details. We make it better looking. We redesign the materials. We get the cost right? All those factors, we do a very detailed design after that, right? All those factors typically happen after the first demonstration or crude demonstration. After that is shown to the customer, right? So, and we ensure that our timelines are in line with the overall business timelines, so that every time we show a demonstration, they can in turn show a demonstration to their customers and keep them engaged. And then the interest stays alive for this technology. Otherwise, I'm sure many people would identify with this. There is a lot of enthusiasm for a new idea at first, but it slowly dies in time. That dies because of this reason, because many scientists, the way they approach the technology bottom up, they will slowly invent one piece after another, and they will put everything together in the end. And if you do that, then the interest will go away in between. So we put things together first, and then we invent the pieces, reinvent the pieces. So that's how this works. Okay. So I think I have given you enough mantras, and we will, of course, summarize once again when we get closer to the end. So I just wanted to, this is a different kind of summary. I just wanted to show that inventing technology requires a complete ecosystem. It is not at all one scientist sitting in a corner and doing what he or she wants, right? It involves all of these people. And academia is one piece, government R&D organizations are another piece, industry R&D providers, that's what we do, contract research is another piece, industry's own internal R&D lab, industry captive R&D, which is, if you're an automobile industry, you will have an R&D lab, which is very specific, which has some equipment to test very specific automotive requirements, right? Which is also an important piece, right? And on the line, on the fringe are IIT Research Park and startups, companies, which kind of bridge the gap between the two. And of course, R&D related services like patent searching, product design, which is how to make a product look good on the outside, and the various manufacturing auxiliary services in the market. So on the other side, the right side, is the folks who buy the R&D. Was industry and government consumers of R&D. So finally, somebody has to buy the R&D and take it to market. When I say buy the R&D, I'm talking about acquiring the intellectual property, acquiring the designs, acquiring the complete protos, and literally funding a program which can transition this to a real product through marketing channels, right? So all of this is part of the technology ecosystem today. And if any of this is missing, it becomes difficult, right? And all these people need to work together, which is also not quite happening. But we need to work together more and more. We as PowerGear have just signed an MOU with IIT Madras for jointly approaching customers, because customers also see a higher probability of success if they see an academic and an industrial R&D organization coming together to offer a project, right? So this is the ecosystem, and it is starting to exist now, right? Not all pieces were there before, but now all pieces are there, and they're actually starting to talk to each other. So this again is something that we do. I won't spend too much time on it to show that we are walking the talk. So on the left you see a lot of skills. So we maintain scientists in all those disciplines in our organization. On the right are the markets that we address. So we combine various skills on the left to meet a given market on the right. So if you take biotech, if you want to build a medical instrument, we combine, for example, materials, electronics, maybe MEMS, some optics, depending on the biotech application. And then we create a team, create a multidisciplinary team. We hear the problem from the biotech company, we solve it for them, right? So that's how it works. Okay, so now I'm going to get into some actual T2P case studies, okay? So these are real examples of technologies that made it into product, and of course product at various phases today, but these are all actual examples. So I'm going to talk in some detail about these case studies, right? And I did see some of the questions that came through ahead of this talk, but I'm hoping that some of them will be answered during the talk and we can get to the remaining after we finish this. Okay, so this is the first case study, which is called tabletop DNA PCR. DNA is, of course, everybody knows, it's the DNA molecule that's inside the body. PCR is a process called polymerase chain reaction, which is a process where DNA makes copies of itself. So it's a process where DNA reproduces rather and makes an exact copy of itself. And the application, right? Again, as I said, we have to start from the application. The application here is called point of care diagnostics. So point of care diagnostics. Diagnostics means you're diagnosing a certain disease in a human being. Point of care meaning the point where you get your care, which is usually the doctor's office. So today, when you are sick, you go to the doctor. Doctor gives you, doctor asks you for your symptoms, and then doctor says you go and do all these tests in the lab, and then you come back with the report, right? So he may ask you to do a certain blood test for XYZ. So all that is written on a piece of paper. You take it to the lab the next morning, and then you get your blood tested, and then it takes about a day to get your results back. And then once you have the report, you fix another appointment with the doctor, and then you finally get the prescription, depending on what disease you have. So that's a typical process. Okay. So the point of care diagnostics is the aim of this application was to put the diagnostics at the point of care. So to put the lab test, which is the diagnostics part, right at the hospital where you see your doctor, right at the clinic, right? So you eliminate this entire 3-4 day cycle time of going to that lab, waiting for the report, going back to the doctor, all of that. So the idea is you go to the doctor, you get everything tested. Right there, you get your prescription and you come back. Okay. And essentially, it's a disruptive idea where you're trying to eliminate the blood test lab entirely. So that is a disruptive idea. We worked with the company on this. So we eliminate the blood test lab. We put the blood test on the doctor's table, literally. So the idea is to make a small, almost portable instrument. And what you're seeing in that picture is about, it's a cube roughly of about 6 inches each side. It's literally that small. and eliminate the cycle time for prescription. So if the patient is willing to wait about 45 minutes, 1 hour for the test results to come, finish it right there and get results and go home. Okay. So how do you do this? Right. That's what I'm going to talk about in the rest of the slides. So first, as we have been saying in the mantras, we have to start from the market. Right. We cannot assume that this is what a doctor wants, this is what the patient wants. We cannot make assumptions on that. So the first step is to survey the market. So I had to talk to a lot of doctors to see if this is something they would buy. Right? If there was an instrument like this, is this something that they would buy? What is it worth to them? What is the willingness to pay? Right? What price would they be willing to pay for this? At least an approximate idea. And that would give us a very good guideline on what should be the cost target once we make this device, whatever this device is going to be. Third is what features are required in the product, right? Do you want, how do you want to put the sample, blood test sample inside this? How many diseases you want to test for? How do you want the results to be shown? Do you want a huge looking instrument, or you just want a cell phone interface? Where you can plug this into your cell phone and you look at it on your screen. All of this is important. And finally, let's get greedy and see if we can do better than a conventional test lab, right? So anyway, we are inventing something new. So why don't we do something that is better than a conventional blood test? So all of this forms the market survey and ultimately the voice of customer. And once this is all recorded, then it starts to create a good problem description for us in terms of what is needed for this innovation and what will sell, right? So if you meet whatever the doctor told you in terms of these features, then very likely the doctor is going to buy it from you. So you have a market. Okay. So next slide. And I'm just keeping this a little brief, not too much detail, but so the next step, once you have all the information from the market, is to, of course, brainstorm the technology concept, right? So how will you do a tabletop detection, which is more accurate than a conventional lab test? So the answer was, in this case, it was a DNA match. Okay. So if usually what the kind of testing that happens in today's blood test labs is called a reagent-based testing. Okay, it doesn't do a very precise match. There is a margin of error. So in many tests, they say that it is only 60-70% accurate, right? Some tests give you false positives, some give you false negatives. So there are issues, right? But it so happens that DNA technology is mature enough today that if you find a good DNA match, then it's a very accurate result, right? So let's say you're testing for a certain bacteria, like for example, tuberculosis bacteria. And I'm choosing tuberculosis because the known tests in today's blood test labs for tuberculosis are not very accurate. Okay, so if you can find a DNA, a fragment of tuberculosis bacteria DNA in your blood, then you can be pretty sure that you have tuberculosis. Okay, because it is not easy to make a mistake in finding the exact sequence of the nucleotides that form the tuberculosis DNA, right? So we chose DNA match because of that reason, okay? And the literature showed us that in about 1 hour maximum, we can do what is called a PCR process. And that process is shown here. I'm not sure how closely you can read it, but you can Google it. PCR is polymerase chain reaction again, and it is the process by which DNA replicates. So the idea here is to find a match in the blood sample for the target DNA, in this case, the tuberculosis DNA, and then make that match replicate itself, make copies of itself. In other words, amplify the signal, because it's very hard to detect just one molecule that is matched. You want to make million copies of itself so that you can detect it. And that process is called PCR. And PCR is essentially a thermal cycling process, right? So if you go one level deeper, PCR essentially is affected by rapidly changing and very precisely controlling the temperature of those cycles. So you swap between two different temperature levels, typically about 60 and 90 degrees Celsius. And then you have a dwell time at each of these temperatures, and the control system which does this. Yes, of course, you need heaters, you need power electronics, you need a control system which is controlling the temperature, and the overshoot, undershoot, all that has to be very precisely controlled, and it has to be done fast because the patient is only willing to wait for 1 hour max, right? And this typically does about 40 temperature cycles in that 1 hour time. Okay, so that was what we honed in terms of the technology concept. Okay, okay. So once we had the technology concept, then the next question becomes, what is the main challenge? What is the main risk in making this happen? Okay, so and now we are talking about technical risk here. Okay, so the main risk in this case was identified as, how do you, again, just as I said in the previous slide, how do you rapidly control these temperature cycles in a very precise fashion? Okay, so then to address this, we do what is called short loops. Okay, and this is a very important part of our research planning. So we don't just start making, once you have the concept, we don't just start making the whole thing, because there will be a lot of issues with the final product or the final prototype, right? We identify the main challenges, in this case, temperature cycling. How do you rapidly change the temperature, hot, cold, hot, cold, hot, cold, right? And so we do what's called a short loop, which is essentially an experiment or a demonstration, which runs only that challenging part of the project, right? So here we only built that temperature cycling part. We didn't build anything else. Okay, how do you collect the sample? How do you detect it? All those things worry about later. So we built the temperature cycling part, where of course, we took some time. We took 2-3 months. We were able to demonstrate a certain hardware and software which could control the temperature of something, of anything, but within the parameters of what was required for DNA analysis, DNA PCR. Okay, so it was rapidly shuttling between 60 and 90. Can you just show that part? Can you just cycle 60 to 90, 90 to 60 rapidly within this 1 hour time scale, right? So this convinces our customer that these guys know what they're talking about. They know what are the important parts of the technology, and they have solved one major risk in this project. Likewise, there was a second key challenge that was identified in this project, which was, how do you detect? What is the sensor part? Which, okay, now you make the DNA copy itself, you run this PCR process, but how do you know whether DNA has matched? How do you know whether it is replicating? All that, right? So here again, a lot of brainstorming happened, and we realized that in the process of replication, you will see in that figure that there is this one H+ ion which is coming out every time a DNA copies itself. Okay, and when there is a H+ ion that's coming out, it's essentially making the solution more and more acidic. So the pH is essentially going down and down. So we just decided we'll go with a pH sensor, as simple as that. So a pH sensor should be a direct indication of real time what is happening in that solution. Is the DNA replicating, right? So that also was done through a short loop. We independently demonstrated just a pH sensor. Can you have a pH sensor which is able to detect what is going on in this kind of solution? So once you had the right word is retired these key risks in the project, then we would start assembling the full piece of equipment, designing and assembling them. Because now we know what are the main risks in the technology and how to solve it, right? And then we made the prototype. Okay, and to make the prototype, you need all these multidisciplinary skills, because now now you've figured out the chemistry, you've figured out the sensing, you've figured out the control algorithm on rapid temperature cycle. Now all of these skills have to come together in terms of hardware, software, measurement. This is the system engineering part, and this is for sure multidisciplinary. And I'm not going to read out all this, but a key part of this is the communication hardware, for instance, because finally that's what appeals to people, right? How do you talk to the cell phone on which you're displaying this, right? And how do you, if you have a nice real-time output, you show this DNA replicating itself through that 1 hour, it's even more exciting, right? Rather than just wait for 1 hour and give a red light or a green light, right? So all those things were worked through. And then there is even the, if you look at the last part one, microfluidic control elements, which is how do you move this blood sample through this thing, which is valves and pumps and small, very, very small ones. And then finally the power supply, does it have to be portable, in which case it should be battery operated? How do you do a power backup in case power fails? All little things that you have to think about. Because if somebody is waiting for 45 minutes and power goes off, then you can't start the test from scratch again. Okay, so all of this was worked through and we made the instrument. And literally it was a roughly a 6-inch cube, and you're looking at a box, you're looking at a little heat sink and a fan on top of it, because you're talking about a lot of heating, cooling that's happening inside. Which means that the thermal management is very, very important. If when you're cooling, especially, the heat from the sample has to dissipate out at a very rapid rate. All of that is important. And if you look at the bottom of that photo, you see a little USB sticking out, which is where the cell phone interface happens. So all of that in this compact form factor, so literally became tabletop. And at our facility, we could test as far as mock blood samples. We were not certified to test with true clinical trials, and there are a lot of other people to do that. So this was a very interesting example. I wanted to highlight this because it has so many different skills that come together. And it also shows how we started in reverse from the customer, work backwards to define what all technologies we need to innovate. And consequently, what are the key risks? How do you retire those risks before you make the prototype? All of those things came together in this project. Okay, another project, which is very different from the first case study. So we made a solar water heater. Okay, and you may ask what is so innovative about a solar water heater? It is available in the market. Already people sell it. So what is so great about inventing this, right? So I will explain that. So even though a solar water heater is available in the market, for some reason it is not very popular. It is something that it has been around for a long time, but not everybody buys it. Let's be honest, right? There are many reasons why people don't buy it. Okay, and then so the first step in this, right, which I think is there in the next slide. Yeah. First step was to survey the market. Why are solar water heaters not so popular? Why do people still, in a state like Tamil Nadu, for instance, which has so much sun, why do people still buy electric water heaters, which is almost a criminal waste of the sun's energy, right? So that was the first question. So the big answer that came out of that survey was cost, as simple as cost. Today, an electric water heater can be purchased for 6,000 rupees, 7,000 rupees. Of course, there are some cheaper ones, some more costly ones also, depending on the size and all that. But that's the approximate range. But a solar water heater is 40 to 50,000 rupees. Okay, so different level. So why should I spend that much more? That is the first question. And that is why even in a state like Tamil Nadu, people are not buying enough solar water heaters. Somebody who may be very energy conscious may be buying it, who is willing to do the calculation on return on investment and break-even period and all that. They may go through that and they may buy it. But the average consumer is not buying it. So the first question that came out of that was, can we bring the cost of the solar water heater to the same level as an electric water heater? Then people will definitely buy it, because then the running cost is zero. If the initial cost is same as the electric water heater, then why not, right? So second thing that came out of the question, why solar water heaters are not popular, is the acceptability. Most people live in flats, and the flat association does not give permission to put a huge water heater. Solar water heaters are large in size, right? And even for a small 2-bedroom flat, you need 100 or 200 liter capacity water heater, which is probably 5-6 feet rectangular in dimension, and it occupies a lot of area. It has to be kept on the roof. So which means you'll have to ask the apartment association for permission to keep it on the roof. And not only that, you have to put additional plumbing to the roof, to that appliance on the roof, which is going to add cost even more. You need to connect the incoming water supply to the water heater, which requires some plumbing. You need to give for the output of the water heater, you need to give a special PVC line which can take hot water from the water heater to the floor in which your flat is. So all of this adds cost also. So it is acceptability and cost, right? So the questions that came out of it was, can we increase acceptability by reducing the size of this to more like a dish antenna, right? Because dish antenna today everybody uses, they don't ask questions. Everybody seems to have a dish antenna. And if it's something at least somewhat comparable to that size, and if the cost can be comparable to an electric water heater, then it may solve the problem. Everybody may buy a solar water heater. Okay. So just, I hope this opens your eyes into how much clarity a market survey can give us. So technically, when you start off this problem, you may not even be interested in working on this because you may think solar water heaters are already there in the market. So what's the point doing R&D? But when you survey the market, these factors will all come out. You will understand that cost is a major issue, right? You will understand that size of the heater is a major issue. You will understand that getting permission, mounting it somewhere is also a major issue, right? And if you will also finally understand that if you solve these issues, then you may be able to create a new kind of solar water heater that may take over the market. It may be a very successful product, right? So with that understanding, this was the technology concept. This came out after a lot of brainstorming, of course, where we decided that we will not go with a conventional flatbed water heater. So if any of you have seen a solar water heater, you will realize that it is fairly a flat thing. It is inclined to the latitude of the location, but overall it is flat, and it is usually made of a bunch of glass tubes which trap the heat from the sun, and the water circulates through those glass tubes. So we specifically decided that for size restrictions and acceptability, we will go with a parabolic concentrator. Okay, so what you're seeing is what is labeled CPC is basically a parabolic concentrator, and something that accepts a large range of positions of the sun. So it is not really tracking the sun, it is not moving along with the sun, but the parabola itself is designed such that for a large number of angles or positions of the sun, the light rather the heat will still reflect in some way and get to the bottom. The bottom is where the heat pipes are, if you can see the figure, right? So the other thing that we designed is we made this solar water heater mountable on the vertical wall just outside your bathroom rather than putting it on the roof. Okay. So this gives you some fantastic advantages. One is you don't need to get permission from your association to put it on the roof because it doesn't need to be roof mounted. Secondly, it eliminates that hot water plumbing entirely. So which you have to run from the roof to your floor, which adds a lot of cost. It completely eliminates that. You just need the plumbing in and out of your bathroom wall. That's all you need. So you need to cut out drill half-inch holes, and then you just insert the PVC, and then you're done, right? So that was the idea here, where we design it. It's typically on the south-facing wall, or could be on the north-facing wall. It can't be on the east or west because the sun moves from east to west. But we could design the angles on the north or south-facing walls such that this could be a vertical wall mounted design rather than on the roof, and it could be very low cost. We designed it out of plastics. We designed all the reflectors out of plastics, right? And we literally got the cost down to 5,000 to 6,000 rupees, which is the cost point of a electric water heater, right? And then, of course, what is the major technical challenge? Can this smaller size and different kind of mounting actually give the same amount of hot water as a typical solar water heater that is available today? Now that becomes the technical challenge out of this. So that, of course, there was a lot of work behind that. There was a lot of design work on designing the parabola to meet that requirement. So we had a target from the customer of how many liters of hot water at what temperature is acceptable for a water heater. Right. So based on that metric, we did simulations. We also did the figure you're seeing on the right. We did scaled down experiments. So we scaled down the whole thing. We made the whole thing smaller, right? And we tried to prove that this can, if it's 10 times smaller, can it generate 10 times less quantity of hot water, right? And once we proved that is when we scaled up and made the full size. And the next page, I will also, yeah. So this is again the multidisciplinary skills that went into this project, where we of course had optics because we had to design the parabola for the reflections. Thermal engineering was very much there. How do you insulate? How do you grab as much heat from the sun and transfer it to the water, right? Mechanical mounting system. We had an optional tracking system, not for morning to evening, but for seasons, summer to winter. Also the materials, which was a very important part of this because that would ultimately determine the cost. So we used acrylic on the reflectors and it actually worked very well. And I will show you pictures of not the final prototype, but pre-final prototype. Let me start from the right side picture. I hope the picture is a little clear. This was just a test setup. On the right side picture, just the blue part is the solar water heater. Okay, the blue part is on the top left of that picture. It's a little bit oversized just for experimental purposes, but you can see the parabolic shape. The rest of it is just water tanks. One is a cold water tank, other one is a hot water tank. That's all. It is just there for experimental. We were measuring how much volume we could collect and how much temperature the heat was coming out. The left side picture is a very interesting picture. I hope I can explain it to you. You're looking into the parabola. Okay. And you're looking into the parabola and there are two pipes actually in the bottom, right in the center of that picture. There are two pipes and you can see two suns. You can see two sun images, which means that the parabola is reflecting the sun and shining it right on those hot water pipes so that maximum heat transfer can be achieved. So the beauty of this picture is you can actually see the reflection of the sun where it is supposed to be, right? Showing that the parabola is designed geometrically correctly. Right? And you can see the surfaces are very reflective, which is why the picture is hard to understand a little bit. Okay. So I hope this also drives home the point that even for a simple consumer application where product is already there, but there are issues, right? Even there is scope for innovation. But then innovation, as we originally said, has to start from the market. Ask the market what is wrong with what product is there today. Hence, what can we innovate? And that dictates the entire technical concept, that dictates how we will proceed to solve it. And just like the previous example, we did short loops where we did like scale down models and all that to prove that there is a solution to this concept. Then we could finally scale up, make the full prototype. And there are again a multidisciplinary set of skills that go into this. Okay. Let me go to the third and final case study. And I have a fourth case study, which is more of an audience teaser, where I am just going to describe the problem and let you use your imagination to think through how you will approach it with the similar mantras. But this one is a complete case study, the third one, right? So this is a very relevant issue today. Electric vehicles are there everywhere. You may have seen the recent news in the paper where the Chief Minister of Tamil Nadu launched a lot of vehicles for garbage collection that are actually vehicles from Power Gear. So We are the ones who sold those vehicles through another contractor to the government. And we are making many more of those. So you're actually seeing those white colored vehicles on the road if you drive around today. So this is a passenger version that you're seeing in the picture. The garbage collection vehicle is the same vehicle, but the seating is modified to have a cargo area, right? So here we had a project. We have had so many projects in electric vehicles, but I'm just picking one, which is how do you design the drivetrain? Okay, in an IC engine, in a normal automobile, the drivetrain is, of course, the fuel tank and the carburetor and the petrol engine and the differential universal coupling. There's a lot of elements to it. In an electric vehicle, it is actually quite simple. It is essentially an electronic controller and the motor. Okay, so the motor is mounted somewhere in the rear wheel or in between the two rear wheels, and the controller has to talk to everything else. It has to coordinate everything. So the controller is the brain, where it talks, it even knows the key position, whether the key is turned off or on. It knows the accelerator throttle position, how much you have turned that. In other words, how much power you're asking for. It knows the brake position. If you hit the brake, then it turns off the power. It knows the battery levels, how much charge is remaining in the battery. And it, of course, is connected to the battery because it transfers the battery power to the motor. It also talks to the motor in multiple ways. There is an input and output to the motor, where it commands, based on all these parameters, it commands the motor as to using a certain pulse sequence as to how much torque the motor has to employ. It also reads from the motor the speed of the motor. There are various Hall effect sensors on the motor, and it reads all of that at high speed because the motor is turning pretty fast. So essentially the controller is the brain, right? So there is a lot of power electronics that goes into the motor, and it has to take decisions based on all these, the key position, brake position, accelerator position, all of that. And it has to give the right pulse sequence to the motor, and it has to take care of protection. If something goes wrong, it has to cut off power, has to give indications. All of those things are done, and that's what we made. So, okay, now why did we make it, right? So that was the first question. These controllers are available for a pretty low cost from China. So you can buy controllers. You just have to contact somebody in the manufacturer in China, and they will send you these controllers for electric vehicles. You can specify what power motor you want to control, what kind of motor, they will send it to you. So the question becomes, why do you need to do R&D on a novel drivetrain, novel controller, basically, right? So there, very interesting it was, because we worked with a customer in somewhere in the Northeast, where they were manufacturing a lot of electric vehicles, and they told us that today they're manufacturing based on kits that they're importing from China, but the controller fails. Why does it fail? If you drill down more, if you ask them further questions, why does it fail? Two major reasons. One is the vehicle is overloaded. Here, the vehicle, which is designed for 4 people, like a typical rickshaw, is overloaded to at least 6 people, because a lot of people are waiting in the bus stand or on the road, and the driver just picks up a lot of people and goes. He doesn't want to leave anybody behind. Okay, and some people have luggage, and for all various reasons, the vehicle is overloaded. Secondly, the road conditions are different. There is a lot more potholes, and especially if it's raining, potholes filled with water. So the motor actually, when the vehicle goes into a pothole and comes out, the motor gets wet. And it's electrical, so that's a major problem, right? And motors are expensive components, and if water goes into it, then it's not a good thing. So for various reasons, the powertrain needed to be re-engineered for India, right? Okay, so now let's forget the motor rainwater potholes for a moment. Let's concentrate more on the overload part, okay? Because that's what the controller does. Controller, if it is designed to supply a certain amount of power to the motor, And if the load is too much, then it just cannot move the motor. As simple as that, right? And of course, all of this has to be done at a reasonable cost, right? So this was the market data. This was what the market told us they wanted for India. They said that we need a controller that can withstand overload. We cannot prevent drivers from taking additional passengers. These are share auto kind of vehicles. But we just need a controller that survives and does not fail. And they were getting many issues from the field where controller had failed and they had to replace. So they were not profitable for that reason. So of course, we took that into consideration. And we did many short loops. We got to the core of what effect overload has on the electronics, right? And that it just sounds like you have to increase the component ratings, but that is going to increase cost. So the main effect was thermal, right? These components dissipate heat, and in an overload condition, they dissipate more heat. And if that heat is not removed from the electronics and sent out to the ambient, to the environment, then the temperature of the electronics goes up. And that's what ultimately seems to cause the failure, right? So that was the main issue. So as again, to use the word short loop, we did a lot of small experiments which demonstrated superior thermal management, right? We also did a very simple change into the software, into the logic of how this is driven, which is the second bullet, which is shown on the slide. So we designed for overload, but not pickup. Okay. So what this means is it's the simple equation F equal to ma. M is more because it's overloaded. There is a higher mass, right? And if you want to maintain the same F, the only thing you can do is to drop A, to drop the acceleration, right? That's the only thing you can do because that equation only has two parameters. It has M and A, right? And you have to design for higher mass. There are more people in the vehicle. And if you reduce pickup, F equal to ma, F will be the same number. And force into distance is the amount of energy that you consume from the battery. And because you have limited A, you have the same force. Force into distance is energy, and you get the same mileage because the battery consumption is the same. Right. So I'm kind of oversimplifying this, but that is the basic logic behind what we did. So we did not allow the controller to give a lot of pickup. Even if the driver is really pushing the accelerator and wants pickup, the controller will not give that much current to the motor, right? Because if you do, then the F equal to MAF goes up and then you draw more energy and then the battery will die quicker. And then the same driver will come back and complain that he's not getting the mileage. So that was the logic behind this, right? So two simple innovations. One is better thermal management. Second is to limit the pickup. Those two together got us to getting a similar performance on the electric vehicle, but it could also work for Indian conditions. Okay. So yeah, this is a little more detail on some of the short loops. What you're looking at is only the rear wheel assembly in the picture with the motor on it. A lot of lab conditions were tested, test conditions were simulated. The controller is on the table. If you can see a PCB with a lot of aluminum pieces. That is the improved heat sink, which dissipates the heat better. Another bad situation was this controller is actually placed under the driver's seat, and there is no vent or anything for airflow there. So still you have to dissipate heat. So there is no convection, there is hardly any radiation. So we had to do thermal management purely based on conduction, and the mounting and how well the conduction happens. All of that was designed as part of this experiment. We proved it in a small scale first, and then we built the full controller. Okay, and of course, this is also multidisciplinary. It requires a lot of control systems for controlling the motor the way we want it to run. As we said, we are limiting pickup, even if the person is asking for pickup. Thermal, of course, is a very big part of this. and electronics, right? Okay, so I'm going to move to the final case study, right? Last 2-3 slides. Again, this is just an audience teaser. This is a very radical project we are working on. We call it kind of next generation artificial intelligence. A lot of artificial intelligence that is happening today is essentially data analytics. So there's a lot of data that's available. People try to put some intelligence, get some trends, make some sense out of the data. That is also AI, of course. But we are doing research, right? So we are doing something else in AI. So we are kind of trying to predict what is going to come next. So this is a project that's called Natural Computing Engines. And I'll explain what that means. So today, if you want to do a simulation on a computer, there are so many different packages that do that. You have ANSYS, you have many other similar packages which use finite element methods or variants of that, right? And the main fundamental behind those simulations is that it discretizes a complex three-dimensional structure that you're trying to simulate. You could be doing a mechanical simulation, electrical simulation, electromagnetic, so many thermal, or multiphysics, which combines all of this. But essentially, as I said, it discretizes. It breaks it up into many small elements, and it runs a simulation. It solves for each element, and then it combines all of that into a single result. So there is a big issue there, right? There is the issue is that these simulations take a long time. Anything even reasonably complex, even given computing speeds today, easily in most practical problems, we have simulations that run for several days. And after running it for several days, you may even find out you made a mistake and then you have to rerun it. So there is an issue with the way simulations happen today. Okay. And that issue is relying on the fact that all of this is based on a finite element technique where it is discretizing, and the more you discretize, the finer the element size, you get a more accurate result, but then it of course takes much longer to do the simulation. Okay, so this is a different way of doing computer simulations. That is what this project is about. It's called Natural Computing Engines, which means we are using nature as a computer rather than using a physical PC. You're using nature itself as a computer. Okay, so the benefit of this is that we, theoretically at least, this can give you orders of magnitude faster processing times in computer simulations. And I'll talk about it in the next couple of slides. What picture you're seeing in this slide is just planetary motion. Okay, you're looking at the sun and all the planets moving around it. And planetary motion is actually a very complicated problem to solve. And of course, in physics, we simplify it. So if you look at the motion of Earth, for instance, you have to figure out all the forces that are acting on Earth. We simplify, we only take the sun's force because we know that's the biggest one, right? So we simplify and we are able to solve the problem that way. But in reality, the Earth is feeling gravitational force not only from the sun, it is feeling it from all the other planets as well. It is feeling it from its own moon. So there are so many forces acting on it. So if you need to solve this problem accurately, it's what's called an n-body problem, because there are n bodies, each of those bodies exerting forces on every other one of those bodies, right? So to truly solve this problem accurately, you need to take into account all of these forces. And if you try and do a computer simulation with all those forces, then it's going to be a nightmare. It's going to be almost impossible to solve in a reasonable amount of time. But nature does it spontaneously. Nature really does it spontaneously. Every instant, given the position of all these planets, nature is able to compute instantly as to where all the planets will be at the next instant, right? So if we were to do it with classical physics, it would take forever for us. But nature, every second, where all the planets will be in the next second, nature is able to compute in 1 second. Right? So the assumption, the premise here is that there is an inbuilt computing engine in nature. There is one way to think about it. And that is how nature may be solving all of this. Right? So what if we can use nature as a computing engine? And we know that nature computes because nature follows the laws of physics. Right? So here is another example where if you have a billiards table and there are a lot of balls on the table, right? And simulating this is again not easy. It's a fairly complex simulation. But once you hit the striker on any ball, in just a few seconds, nature is able to compute the positions of all the balls on the table, and literally nature puts those balls there, right? So in just a few seconds, nature is able to solve this problem. Okay. So I'm giving you another very simple example, just to drive home the point. Everybody knows that if you drop a ball from a certain height, 1/2 gt square, g is the acceleration due to gravity, t is the time, right? Time taken for the ball to fall from height h to the ground. So h is equal to 1/2 gt square. Everybody learns this. It's an equation of motion, right? So the important thing to recognize is that there is a square in this equation. Time is squared. So if you look at it on the right, if you want to use nature as a square root calculator, right? So we are making an assumption that nature has an inbuilt square root calculator in it. And again, this is just an illustrative example. Today, calculators can calculate square root very fast, but I'm just trying to explain how nature can also do it, right? So if you want to calculate square root of 2, you drop the ball from a height of 9.8 meters, and you simply measure the time using a stopwatch, right? Measure how long the ball takes to fall down. And that number will be square root of 2, right? And so nature has calculated square root of 2 for you, right? Which means somehow, somewhere nature has a square root calculator, okay? Similarly, there is another, if you want to solve a second order differential equation, for instance, right? And second order differential equations, again, a little complex to solve. There are things in nature which follow second order differential equations. For example, if you rig up a simple circuit with an inductor, capacitor, resistor, then the solution, the voltage, instantaneous voltage at any point in that circuit follows a second order differential equation, right? So you can think of it in a different way, where if you want to solve your own second order differential equation, you can choose an inductor, capacitor, and resistor of the appropriate coefficients of that equation. And then you simply run the circuit. Instantaneously, you will get the solution by measuring the voltage wherever you want. That is the solution of that second order differential equation. Okay. So as I said, this is just a teaser. This is simply to fire your imagination. I'm just going to post some questions on this. I'm not going to give you all the answers, right? How will you extend this idea into real applications? Okay. Now, as we always said, we have to think in reverse, start from an application and see how the idea can be applied. How do we, and obviously this is going to have a multidisciplinary approach, right? And how do you make it completely application oriented? Right? This is just a simple challenge for the audience to think along these lines. So I've given you a very exotic, far out idea, almost a crazy idea. And I'm trying to push you to say that can you apply these mantras to a new idea, which is out there, right? And can you find a real application? Can you think in reverse and can you define a problem which utilizes something similar to this idea, right? So that's the challenge. Okay, so I just wanted to summarize. So a lot of mantras were discussed today. It's a fact. I mean, there are gaps between academic and real world R&D. Okay, all of us came from academic institutions, even though I'm a scientist who works in industry. My BTech, my PhD, everything was from an academic institution. So there's no denying that, but I had to unlearn and relearn a few things, right? And the mantras that you saw today, working in reverse, think product oriented, think multidisciplinary, all of them sound simple now that you heard it, but implementing it is something else. Okay, so, and these gaps are real. They really exist. And once we acknowledge that, I think we can improve. And these gaps can be bridged. And I think one very simple way to bridge these gaps is for all of us to collaborate. Right? I showed you one slide on the technology ecosystem where all the components to do real R&D exist here today. Right? And if all of us can collaborate, government, academic institutions, industrial R&D labs, I think we will enforce on each other the kind of thinking that is required to make the R&D really see the light of day. And that is the need of the hour, because that is what everyone is asking for. Academic institutions are always lamenting that their inventions are not taken to market, and there is a reason for that. Government wants industry to participate, but there is not much clarity on exactly how industry would participate in R&D programs. They are just saying cost share. Yeah, giving money is one thing, but truly participating, truly doing the research along with academic teams from industry, right? That would be the real way to participate. So in my opinion, I think you need true collaboration, and that will result in a win-win for all parties, for government, academia, and for industry. Because industry will also see a lot more innovations come out that way. Right? So with this, I just want to close the lecture, and then we can take questions. I know there's a list of questions. If Sujata wants to kind of highlight a few, we can start with those, or we can also take audience questions.
Yeah, we'll do that. Thank you, Dr. Subramanyam. I think all your case studies did reiterate those 4 to 5 mantras that you mentioned. And the questions were also in, I think some of these questions would have definitely got answered with the course of the presentation. I'm just putting up the PPT, just give me a second. Meanwhile, for the participants, if there are any questions, kindly do type it in the chat box.
Should I unshare my screen now?
Yeah, can you stop the share?
Yeah, I just did, yeah.
So all of you can post questions in the chat box, or if there is any specific question to be asked to Dr. Subramanyam, I think you can raise your hand. I will unmute you and you can ask your questions, but just ensure that the question is brief and your audio is also clear. We wouldn't want to be troubleshooting the audio problems. You're able to see my screen, Dr. Subramanyam?
Not yet.
Not yet?
Yep.
Yes, now we can.
Okay, so do you want me to read it out, or you're picking up the question and answering? How do you want me to do it?
Okay, let's just go in sequence. And if it's potentially answered during the talk, then we will skip it. Okay, the first question is, please suggest some tips on incorporating R&D techniques in final year academic projects, right? So yeah, so this is, I think, hopefully partly answered. In fact, one very interesting thing that I do personally is I do a lot of mentoring to college faculty and final year students. And I kind of try to drive home some version of the same mantras. I mean, we'll have to be practical and get a final year project that finishes on time. But I think to the extent possible, right? If people can identify some application and start from there, that will be the right way to do this. And in the world of startups and stuff today, I mean, you never know, because some of these final year projects, if they truly start from an application and you work in reverse and innovate something, you may even be able to spawn a startup that comes out of this. Right? So why not? Sorry, somebody was saying something.
No, I think it was just a disturbance. Yeah.
Okay. Yeah, I think number 2 was answered in fair amount of detail during the talk. Yeah, okay. So number 3, yeah, that's a very relevant question. How to ratify the startup idea / model? And I think that was also been partially answered. How to approach investors. So investors also think like this. So again, an investor thinks of money first. An investor thinks of, and most investors ask you the question, can I make 10 times my invested money in 5 years and exit the company? I don't know if it's the right question to ask, but it's the most often asked question by most investors. So unless the market story is crystal clear, then you simply cannot answer the investor. So the investor is going to ask this purely financial question. How can I make 10x my money and exit? And the only way you can answer that question is to show the sales of whatever product you're trying to make, which will kind of feed that 10x revenue kind of question, right? So there is no other shortcut to this except for essentially doing to death market research, which is so clear that I mean nobody can question it. Right? Okay, how to have a successful proposal and have collaborations with top researchers. Yeah. So, this is a very interesting question because I have a lot of experience in this. It's going to be a little funny answer, but I have found that if you have a very interesting idea, and again, interesting idea depends on so many things. It depends on how interesting the application is, how in terms of money the market opportunity is. All of that is included in constituting an interesting idea. But if you have an interesting idea which includes all of these factors, then I have found it's like building a temple. When you build a temple, the money comes. You don't have to ask for the money. Somehow, somewhere, the money comes. So when you have an interesting idea, when you start talking about it, I have found that the collaborations also automatically come. Top researchers will find you, right? So I think we should not be hero worshipping and saying that this person is very famous, I want to work with him or her. I think the opposite question is the one that needs to be answered, right? So what successful proposal can I have so that people want to work with me, right? And I think it will actually truly happen if you just need to try it out. Somebody has raised their hand.
I don't see
I saw
it.
a hand raise.
Yeah.
No, I don't see it right now.
Oh, okay. Okay, I'm looking at maybe question 6, difficulties faced in evolution of a product. And this is also an interesting question. They talk about 2 valleys of death. 2 valleys of death when you have a startup. The first is the technical valley of death. Second is the product valley of death. And most startups, they say, cross the technical valley of death, which means that they actually manage to innovate the right technology and they are successful. But most startups die in the second valley of death, where they have not thought about things like cost, reliability, supply chain, and all that upfront. And hence it becomes an afterthought. And now it is too late to go back and change the technology to adapt to all these requirements. And that is what happens, right? So this is the main difficulty that's faced in the evolution of a product, where it is the cost, reliability, supply chain, manufacturing becomes an afterthought, and it is not part of the initial concept phase. Yeah. So I think, number 5 I skipped. What are the future upcoming ideas for biomedical engineers? I am not a biomedical expert, but I will answer this slightly differently. I will say that we have personally found a major gap in the biomedical industry on the instrumentation side. So we have found that the biomedical industry is filled with excellent biology and medical people, but it doesn't have the engineers. Okay, so it's the easiest way to put it. Where it's either an engineering company or a biomedical company. And if you can mix the two and truly form a biomedical engineering company, I think there are very few of those today. Where if you can there is hardly any medical instrument that is made in India today, almost nothing. Right? Even if you take a simple mechanical instrument like dialysis, it's not made in India, it's imported. So having the engineering skills while understanding the biology part and being able to make machines, make instruments, that alone is a winner today. Okay, I think question 8 seems to be a very interesting question. Yeah, but I think it was answered during the talk, right? The question here in question 8 is essentially, I don't know where my interest lies and I don't know my place in this world. And it is very simple. The question is to find out what are the problems in the world, right? Which one interests you, and start from there, work backwards, right? If Chennai has a water problem, that's a start, right? How do you solve the water problem without lorry tankers, without rain? So what is the ideal solution for water, right? And I think that is how the solutions on these atmospheric water generators came up, where you can extract water from the air. So you're not dependent on rain, you're not dependent on lorry tankers. And the only infinite source of water is the sea. And the sea replenishes the water vapor in the atmosphere continuously, especially in Chennai. And that is all. Literally, it is an infinite source of water. They have measurements on how many billion gallons of water vapor are there just on Chennai atmosphere. And if you can find a cost-effective way to extract that, right? So all these innovations, where your interest lies, starts from the problem, right? And today, and I'll give you a little, maybe another teaser on these lines. Think about it, right? Today, when you extract water from the air, the way to do it, there are few machines which do it, but the energy cost is huge. So it's not practical today. But the way to do it is to cool the air. And when you cool it, just like an air conditioner, water drains out, right? When you cool it, the air cannot hold that much water anymore. So the excess water naturally comes out. So you're creating water from air, right? That is the most common way to do this. Okay, but let me fire your imagination a little bit. Cooling is a very expensive process. So if you're running an air conditioner to extract water, the cost of water becomes very high. So if you think about it, when you have water, well, let's say you spill a little bit of water on the table, because the water evaporates from your hand and it becomes water vapor into the atmosphere. Now you would have noticed that just like sweat, when water evaporates from your hand, it cools your hand. Okay, water cools your hand, which means the water needs energy to evaporate. It is taking that energy from your hand, right? It is taking the heat energy from your hand. It is becoming from liquid, going from liquid to vapor state. And that is a process which is endothermic, which means it is taking energy from the environment. It is going to a higher energy state, and it is therefore. Can you hear me?
So, Dr. Subramanyam?
Yeah.
Yeah, sorry.
Yeah, somebody was muting. Yeah. Okay, so I was trying to say that when water spontaneously evaporates, it is taking energy from the environment and it is going to a state of higher energy, namely vapor, from liquid to vapor, right? So, which implies that if you do this backwards, if you condense vapor to liquid, you should get energy. Because to move liquid to vapor, water took energy from you. So if you had to do the reverse, water vapor to water, you should be getting energy in the process. But if you're going to run an air conditioner and extract water, that you're using a lot of energy. You're giving the water vapor a lot of energy. But scientifically, the physics tells you that you should get water for free, and you, as a bonus, you should get some energy also from that. Right? So theoretically, you should be able to make an atmospheric water generator where you get free water and you get more energy as a bonus. That's what the physics tells you. So think along those lines. Maybe there is a startup idea there. Okay, I think maybe we can just open up the floor to questions.
Any questions? I have not received any questions so far in the chat box, Dr. Subramanyam. Participants may use this opportunity to raise your hand, and I can unmute you and you can ask your questions.
I think if one person starts, there will be a lot of questions.
Right. So that one person has to start.
Sujata, give them an award. The first person who is asking the question.
Yeah. So the PALS champion has said that. So the first person to get to ask questions will be recognized.
I can't be the only one doing the talking in the call. So.
I'm sure a lot of you would have come with quite some, questions in your mind. I like that question on saying that, I'm unclear about what I could do, where I could get idea. So I just made sure that the question remained for Dr. Subramanyam to answer. And that was a question most of you will be having. So is there any similar questions that is running in your mind?
Yeah, it can be any question. It can be right or wrong. That doesn't matter. Please feel free to ask.
How to know my project is good or bad? KIT, Mugendra Nath.
Yeah. Yeah. So the very simple, straight answer to that question is if someone wants to buy, then there is value in the project and it's worth something, right? If nobody is interested, then it's not worth anything. That's what they say when you do an MBA. They say that the price of a product is what the customer is willing to pay, not what you think it is worth. So likewise, the value of a project is what if somebody else is interested in it. So the only way to find out is to go talk to people. If you're doing something in agriculture, do go talk to farmers. If you're doing something in electric vehicles, go talk to drivers. Yeah, somebody, Abhinav Ranjan.
Abhinav?
Hello, sir. Can you hear me, sir?
Yes, we can. Please go ahead.
Go ahead.
Yes, sir. I'm the one who asked that Netflix question. Sir, I have another question, sir. I want to know, what do you think about the super app model, sir? The umbrella models. There are recently many CEOs have been commenting on that. And, sir, since I do not have any particular clarity, I have an umbrella amount of clarity, sir. I want everything in one app. What do you think about the super app model, sir?
Can you explain that? I'm not familiar with that term. Can you just explain that for the benefit of everyone?
So consider an app which will allow you to buy pantries, clothings like Amazon, which will allow you to order food from restaurants like Zomato. And it's sort of like integration of the different type of apps, which will allow you to also book taxis and book restaurants like Oyo, something like that.
Okay, I personally think it's a great idea. I think it's the next step in the evolution of apps. And I mean, when apps came, all of us had a few apps installed, right, in our cell phones. But when there are so many of these, and I'm totally confused as to what apps I want, which ones I use for what, I think the super app concept sounds very appealing to me personally.
Yes.
Actually, you can find the demonstration when you book tickets, and in today's airline thing, they even ask you whether you want to reserve a parking lot, whether you want to book a hotel if there's going to be a long layover. I think it's combining a lot of things. If you look at
agreed. Yeah. I bought some property recently, and I had to learn so many things, legal aspects, how to deal with electricity board, how to deal with metro water, how to deal with property tax, how to deal with registration. If there was a super consultant who can explain all of this, I would be extremely happy.
Fortunately, we buy only rarely. It's a rare occurrence, and then we have to
Yeah.
learn everything at that time on the job.
Exactly. I was just giving a tangential example. That's all.
Yes, sir. This is one way of seeing it, sir. But like recently, Hike founder Kevin Mittal also commented that these models won't work in India because there is so much competition that an umbrella app would not give the same user experience to an individual like which the separate apps can give.
Yeah, but those consumers will simply install the separate apps, right? So maybe there is a place for both.
Yes,
Maybe, right? So it's like the airline industry, right? Boeing and Airbus are the main plane manufacturers, and Airbus started making the huge aircraft, right? They thought that people will want to fly direct flights for long distances and directly go to where they want to go. But Boeing started making smaller aircraft because they thought people will do the hub and spoke model, where they go to one major hub and then take another flight to go to a smaller place. In the end, it happened that both had a place in the market. Some people wanted to fly direct, non-stop. Some people were happy to take 2-3 flights and reach their destination. So I think there is a place for both, honestly.
Okay, Abhinav, I think you got your questions answered. And I think, 191 participants have now started thinking about the umbrella app.
Yeah.
Balaji, you might want to unmute yourself. Balaji from Sairam.
There's one Andrew Dave.
I'll read it out. Balaji, you have to unmute yourself and speak.
I unmute him.
No, I can't. I've asked him to unmute.
I can. I'll do it.
Yeah, because for me, it just gives me an option, ask to unmute.
I have done unmute. But it is not unmuting. I don't know why.
Yeah. So just Balaji, you figure it out, or you type it in the chat box if you're having an audio problem. Andrew Dave, I think it must be a faculty, I suppose. Sir, you explained about using nature as a computing engine, which was very interesting approach. Where is it currently implemented in real life scenario as a complete system, like with the hardware?
Yeah, it's not. Thank you for asking. It's not. It's purely an idea at this point, which is why I throw out the challenge to the entire audience as to where you can take it, how you can think of it as a system, what application can you find. It's just a seed of an idea at this point.
Thank you, Dr. Subramanyam. Andrew Dave, I hope that answered your question. KPREIT Sudan, he's a student. His question is, from where can I know the previous registered patent in a particular topic so that there will be no problem product launch in future? I think
that is very easy. There are lots of, you can just Google, there are lots of tools which will do patent search for you. The best place to start is the USPTO, which is the US Patent Office website. So that should have that is free, and that is has a huge library of patents, of course, US patents, but US patents are a great place to start. There are paid tools, paid search tools also, which if you Google, you will find many of those. There are some very interesting tools which show backward references, which are very powerful. Backward references means that which all patents have referred to this patent. So forward references are just the list of references that are in this patent, right? That is easy to find if you read the patent. But backward references is where these tools literally read all the patents in the world and then they refer back. So what all have referred to the patent that you have referred to, and that can give you a lot more information on, who is working on what in these fields, right? So there are free tools like USPTO, there are paid tools also, depending on how much you're willing to pay. Just like the where you search for publications, no? There are very similar tools.
There is another question from Kevin Raj from Sona College of Technology. His question is, sir, is it possible to connect turbine with car tires and can we produce electricity to recharge the electric vehicle?
Yeah, okay. This is a very common question. You are violating the law of conservation of energy if you do this. Think through it. So you're doing a perpetual motion machine, which is impossible according to the laws of physics. So you're saying that you will run a car with electricity, and from running the car, you will charge the battery, right? And it just won't happen. So because the net efficiency is less than 100%. And if you try to extract energy from the running car, you will not get enough energy to recharge the battery. It's as simple as that. So this is just, everybody has this doubt, and it's good to have this doubt, but it's something that will openly violate the laws of physics.
Do we have any more questions? Balaji from Sairam, are you still there?
Sairam is Sairam Engineering College?
Sairam, yeah, institution. Sairam College Institute or Sairam Engineering College, one of it.
Okay.
We have both of them.
I had a gym trainer who was a fresh graduate of Sairam Engineering College.
Nice.
I'm saying this in a positive way because he was able to explain all the exercises to me in a very technical way as to how each one will benefit. So that is a very classic multidisciplinary thing, where you can combine exercise and technology, and it actually really made a difference. He was truly able to tell me why something would work.
Talking your language, essentially.
Exactly.
Sujata,
So
will we
I
have
think
any
we
questions in YouTube? Will there be questions in YouTube as well?
No, there is nothing. I just checked.
Okay, thank you.
So I think we will, okay, last one. There's one more question.
Anup Kumar.
Do you think creativity plays a major role in making theory to practice possible? It's actually today it's technology to product. We should stand corrected in the real world, or is it just the necessity and need of the hour that makes theory to practice possible?
Yeah, no, I think creativity plays a huge role. So all I was saying in the talk that is that the necessity should come first in the sequence of events, right? If you create first and then look for necessity, then it may or may not be necessary in the market. But if you look for necessity first and then you innovate, then that will work wonders. That's the magic. So it's simply the sequence of events. So very much creativity has a huge role. And finally, the innovative solution comes from creativity. There is no question of that at all. So great question. Thank you.
I'll just pause quickly for 30 seconds. If there are any more questions. Thank you, Tarun Kumar.
Any more questions?
Is it possible to split carbon from CO2 and use the extracted carbon as a fuel for vehicles? By doing so, we can also reduce the air pollution.
Okay, great question. Yeah, this question is something I always talk about in school lectures, high school lectures. See, it's very simple, right? When you say C plus O2 gives CO2, so when carbon becomes carbon dioxide, that is an exothermic process, which means that carbon plus oxygen giving carbon dioxide has a lower energy versus carbon and oxygen. So the difference in energy is what you get by burning the fuel. So the fuel usually is a hydrocarbon. It contains carbon and hydrogen. The carbon part becomes carbon dioxide. The hydrogen part becomes water vapor. So both are exothermic processes. Carbon becoming carbon dioxide, hydrogen becoming water vapor, right? And that is why you get energy by burning a fuel. So it follows that to convert the carbon dioxide back to carbon, you have to give energy, right? That's how nature works. So if you give energy, you can convert carbon dioxide back to carbon, which is exactly what plants do, right? Plants take in carbon dioxide, they give out oxygen. What is left is the carbon, and that carbon is used to grow the plant. It is forms hydrocarbons, and it's used to grow the plant. It forms the fruits, vegetables, stems, whatever, right? That is how the plants are converting carbon dioxide to carbon, but the external energy comes from photosynthesis, comes from the sun. And you cannot do this process without giving energy into the chemical reaction, right? And this is what plants have done for thousands of years. And of course, we are all reversing that, converting the carbon back to carbon dioxide in a couple of centuries. So yes, so the need of the hour is to do this, but the only way to do this is to give energy into the chemical reaction.
So then this question again, government says 2030 most vehicles will be e-vehicle, but if you can make biodiesel vehicle available for vehicle on road in 4 to 5 years, does it economically be benefitable? Benefit.
Yeah, so it's a great question. Government, yes, is saying that, but the practical thinking is that until about 2050, there will be hybrid vehicles, which will be partly electric, partly based on alternate fuels. And alternate fuels are not, biodiesel is certainly one of them, because you have biological waste products from which you can extract useful fuels. There is also hydrogen fuel cells, methanol fuel cells. They are all options. There will be those technologies along with batteries. So it will be some form of fuel, and it will be electric. That is the current thinking, that practically speaking, until 2050 or so, there will be hybrid vehicles. So your thinking is very much in the right track. If you have a good idea on a hybrid technology, when I say hybrid, fuel plus battery, that's what it means. And that fuel, of course, has to be something unconventional like this, which is from sources that are not from petroleum, right? Which will make it more viable and less and more cost effective, right? So that is going to be there for the next 30 years. So I think this is, if you want to think along those lines, it's actually a great idea.
I think if you have any more questions, you can write back to us and we'll see how it can get answered. Thank you, Dr. Subramanyam. I think as always, it was very delightful and very insightful to have you with us. I would now request Subbu, PALS champion, to give the concluding remarks and vote of thanks. Subbu?
So I cannot get a PALS mug memento this time. So
no, we'll get you something. Don't worry.
Virtually, we are giving you something, Dr. Subramanyam.
Thanks for asking us. Thank you very much. I think many students would have heard this small, monthly magazine called Reader's Digest. Most of you, probably some of you would have read it also. So what Reader's Digest does is, there is no original article in that. What it contains is all condensed articles from various sources. In the last 20 or 15 pages, even a novel will be condensed and given. It's a great book to read once, it comes once a month. In the same fashion, what Dr. Subramanyam has done today is really given in a digest form to all the students, including me. I'm telling you that how from a concept you can get a product out and what are the steps. Whatever, assuming, let's say he has got 20 years of experience, he has condensed that in a 2-hour presentation, methodically explaining to you how, the TTP, he has even rechristened this as technology to product, how that can be achieved. And what are the different stages that you have to go through. And plus, he has demonstrated the use of those techniques, what he described in all the case studies. I think it was an excellent presentation, Dr. Subramanyam. Thank you very much. It was really an eye-opener to many of the students. And all of you who are involved in Innova projects and the entrepreneur cell in each of the colleges, I strongly recommend, I think this is being recorded. I think next 2 days it will be made available, the link. I think you should all of you listen to this talk, because let me be honest, it's very difficult to get such ideas in a condensed form, and that too from a practitioner. Be there and done that type of a person who is giving it to you. So the chances of you going wrong is very low if you follow what he has said. I think he has done a phenomenal job, and as Anu said in the beginning, he has been a great pal of PALS. I have visited his factory in some maybe 4 years back, and he has participated in Innova and all of PALS offerings. I think that shows his, other than what professional work he is doing, he also wants to help the student community and the technology ecosystem. Thank you very much on behalf of PALS. We really enjoyed you, and we hope to have a long association with you, Dr. Subramanyam. Thank you very much.
Thank you. Thanks a lot.
Thank you.
Sorry, one more thing I forgot. Actually, it is real support from the PMO office of PALS, which they really do a lot of that work.
Thank you, Subbu. Sure.
Mute padidu para.
Seriously, because otherwise we can't get these things done. I think I want, and also the student leaders and the faculty member, EC committee members of PIs who have also contributed. Thank you very much.
Thank you all. Robin has been posting constantly couple of forms. So it is just 2 forms. Do not get psyched out seeing so many links. It is 2 forms. One is a quiz link and one is a feedback link. Quiz link, copy it. We'll anyway send a mail to you. So don't worry about it. But feedback, ensure that you give it then and there. Your feedback is the only source for us for our continuous improvement. So, do that. And I did see a couple of 2 questions which we might have missed. We'll probably take it up at a later point in time. We'll see if we can get it answered from the speaker later.
Okay, then. Thank you.
Thank you all.
Subbu.
Thank you for
Thank you,
being
Subbu.
here. Thank you, Subbu.
Thanks a lot. Bye-bye.
Thank you, Anu. Thank you, Dr. Subramanyam.
Thank you.